you go to Netherlands, I think they have have the high skill expertise in hydrogen in Europe. Of course, because they are a tiny country and they have to take care of their groundwater resources, but also they have shown very skilled competence in groundwater. An example, it was the Dutch technology that was designing the largest geothermal installation in Norway at Skardermoen in 94. So, welcome, it's nice to have you here.
Thank you for the introduction, Kirsti. Yeah, my name is Robert van der Ven. I work in SWECO, Norway. I have experience in the shallow geothermal energy business from the Netherlands, where I mainly design groundwater-based systems. And here in Norway, it's more like borehole heat exchanger type systems. I present on behalf also of Hafslund Oslo Celsio. They own the project that I will introduce. It's a project where they will build a high temperature seasonal storage for waste heat storage. The plant storage temperature is up to 95 degrees. And the project was started by Fortum Oslo Varme, which was later bought by Hafslund in 2018. And a Swedish company called Sense performed a feasibility study. They concluded that it was feasible to have a high temperature storage with borehole heat exchangers in the area that they had in mind. Rudena, as a Norwegian company, followed up with a more detailed design. I worked in Rudena before, switched to SWECO. And SWECO has been involved since November last year to look into some practicalities and how to solve it. So what I will present to you is a little bit about the project, about some design considerations, the cost price per kilowatt hour, and the local environment, because in the end, the client came to us with the question, how can we best present to the board of the company what type of design, so the configuration of the well park, what is best, and what's also in terms of risk, reward, total investment, and the approximate cost price per kilowatt hour that we can retrieve. Because in the end, it's all about the money. If it doesn't make sense from a economical viewpoint, then it's nice about the environment, but then usually doesn't come through with such projects. And I will also discuss like a local environmental impact, like storing 95 degrees will not happen at like 100% efficiency. You have an amount of heat loss, and what does the heat loss and what will be the effect? So the project is located here in east of Oslo. About here in the south, Clemensrud, there's like the main waste incineration plant of the district heating company. They produce or they burn waste throughout the year. They produce electricity and heat. They can sell the electricity throughout the year, but not the heat, because there's very little demand during the summer. And it actually costs them a lot of energy, a lot of electricity to get rid of the heat, because they have to use dry coolers or dry cooling towers or whatsoever. And what they would like to do is have a storage facility that also reduces the cost of getting rid of the waste heat, and then it's a plus if they can retrieve some during the winter. So the benefits for them is it's a cheap method for dumping waste heat. It also reduces, as also presented by previous presenters, that you also reduce some of the peak load needs. The peak loads are now covered by the city district heating company by electricity and fossil fuels, and both are like unwanted. So it's nice if we can reduce the need for electricity or gas or oil. In addition, we save some CO2 emissions, and the electricity can be used for other purposes. It's a project, and each project has its own specifics. Here it is that the plot is not owned by the city district heating company, it's owned by the municipality, and they have given a lease of the plot to the city district heating company, but they had some requirements as well. So we have space limitations, and the space limitations means that we can only use 16 meter in diameter on the surface, plus some additional room for the insulation. So it's planned here. There's currently on the side they are constructing a nursery home. Here are we going to have the well park. This is also how the configuration will be: 173 wells to 150-meter depth. And here we have an energy central. This area is higher in elevation, so about 8 to 6 meters, and it's like an decline elevation here. And then we have a flat field, which is currently used as a football field, and they will continue to use the area as a football field after the completion of the well park. And it's only possible to have such a system because they also have planned a low temperature district heating network that will feed new buildings, but also existing. The temperature to the client, so it will be, it's designed for a 70, 50 degrees Celsius network. So it will supply 70 from the energy central, and the planned return temperature to the energy central is 50. So the well park has to supply 50 degrees or more because they are not planning to use a heat pump. If you would use a heat pump, you could increase the efficiency, but it also increases the electricity need. And they have a nice system for waste or thermal waste energy storage, but the main goal of the company itself is reducing the cost of getting rid of waste heat. So if they can retrieve some of that waste heat during summer, then that's just a plus. But of course, for us, like SWECO and when I worked in Ruden and Sense, it's like our goal is to have an efficient storage as possible. And one of the challenges is the borehole heat exchanger, because we are going to store up to 95 degrees Celsius and like a high temperature, and plastics are not two things you usually combine. So they're working with a Norwegian supplier. They have now a borehole heat exchanger, and they're having a research project to also find out what's the exact life expectancy. The minimum requirement was 30 years, but of course it's a plus if we can increase that, because we will install 52 kilometers of plastic tubing in the subsurface. And it would be nice if we can use it like for a very long period, because in the end, if it only works for 10 years, then we create also a lot of pollution. And one of the things we have to take into account were the nearby buildings and the trees. And then, yeah, if you ask me, they're not special, but those trees are very valuable for the municipality. So they want to keep them. And that's a challenge for us, because we're gonna, create something which potentially reaches like 83 degrees. And we have trees here, and if it's like 80 degrees here during the winter, and it's minus 20 outside, then how will the trees cope? And we have some thermal pollution, of course. We want to reduce that as well. And another requirement for municipality is that it's not visible during the winter, that there's an actual storage there, so no snow melt. And something about the local hydrology. It has the area has about between 3 to 15 meters of clay overlaying bedrock. So underneath the clay we have directly bedrock, but it's different geologies, and the top of the bedrock is also wetted. So we have a lot of small fractures there. And that brings some challenges, because the wetted bedrock can potentially result in leakage from groundwater in the bedrock into the clay. And that will drive, like, increase the losses, thermal losses, and thereby reduce the efficiency. And one of those potential drivers for losses is groundwater flow, and that can be flow from like a high pressure area to a lower pressure area. So for example, from the north to the south, which in this case is not present based on the thermal response test that we did. But there is something called the thermal like the density driven flow, which is pictured here. It's from Scarpagen and all, 2019. It's really nice. If you heat up water, it decreases in density, and as everyone knows, heat tends to rise up. And if my warm groundwater is able to leak on the top, and we have fractures in the bottom, which is the case in our project, then we would replenish the hot water that leaves with cold water in the bottom, and that would, first of all, create thermal pollution at the top, but also reduce the efficiency of the storage. So in feed flow, we have performed a simulation to find out, okay, what can we expect in terms of groundwater losses? To give you an idea, if you would have a 100-meter borehole with a 100-meter water column, which is in in this project also the case. We have a bit of artesian flow, so it's all the way to the top that we have the groundwater now. If we would heat that 100-meter water column, which is 10 degrees at the start, to 95 degrees, then it would rise by 3.5 meters. It becomes lower in density, so it means that you have a little bit less pressure, or like a lower density, and especially if your water leaves at the top, it means that the water has to be replenished from the bottom, and that can be a big driver for leakage and thereby thermal losses. So basically, if we heat it up like an electrical boiler, the water tends to rise, the heat tends to rise to the top. So yeah, the different distribution. So it's coldest in the bottom, it's warmest in the top. And if in the top my water can leave, then we have a problem. That can be either through by the bedrock, or it can be maybe a leaky well casing, it can be a leaky well top, and so on. So we need to be sure that everything is tight, and we cannot control the geology, and we have an idea, and we do think that we understand it, but of course it's always surprises when you actually start building the project. But we gave it a try. These are some of the results. So what you see here, this is basically the groundwater flow vectors. We have a well part here. It's the box model. So this is basically bedrock. We have for this depth, we have a fracture zone. So we have a simulated a fracture that was measured by Rudena and stream well logging. And then here, in this case, we have a top which is open, so water can flow up, and we allow the software as well to have different groundwater densities, which could change with temperature. So we started warming up the groundwater, and it wanted to, so it's in simulations, it wants to flow up. And in this case, it can freely flow up and it can freely leave the simulation. And then we see that there's a replenishment, especially from this side, with cold groundwater. And then here you have this distributed, like shown in the groundwater pressure distribution. So the lowest pressure here, and which leads that water is drawn from the sides and then flows up, which drives the potential loss, which, if uncontrolled, will be 145 cubic meters a day. Doesn't sound much. If you think that it's like on average maybe 70 degrees Celsius, that's quite a bit of thermal pollution. And if uncontrolled, you will talk about 1.5 gigawatt hours of thermal heat loss. The project is planned to deliver between 5 and 5.5 gigawatt hours of thermal energy once it's stable, and we're planning to inject about 7.8 gigawatt hours. So it's 1.5 gigawatt hours on that scale. It's quite significant. Two colleagues of mine, Patricia Monso, and also with assistance of Göran Hellström, they performed also simulations in Francis to find out, okay, what is the expected efficiency of such storage? Because we know the investment cost for each configuration, and we also want to know what is the efficiency. So what did we do for Celsius? We compared 7 different configurations for the well park. We have a constraint in size. And so we looked into, okay, we have a maximum, like basically volume that we can use. What if we have different borehole spacings? How many wells can we fit? So that's quite significant. So if we would drill with 3 meter spacing, we could fit 341, but if we only drill with 5 meter, it's 129. So it's significant. And the volume that we would use is the same. It's the ratio of bore heat exchanger density versus volume that changes. So if you would have more boreholes, the total storage capacity of the storage itself is not much bigger, but the effect that you can deliver is bigger. But if you have such a system with more heat exchangers, you can theoretically supply more energy in the beginning of the winter, but then you run the risk that at the end of the winter, you're out of energy. So we also have to find a balance between that. The storage is not infinite. You have a certain volume, and we can store a certain amount of heat energy. This is the alternative that I've chosen. It's like the right mix for Celsius between storage volume, effect that it can deliver, and also the financial risk in the total investments. The board of directors will make a decision in after summer. We expect that it goes through, and then they will start building most likely after Christmas. And one of the things that we did is okay, what is the amount of energy that we can supply? This is like the heat transfer rate. So you see during the charging, this is the temperature of the storage, the orange one. It's like it's relatively cold, so it's about 56 degrees. We're going to inject about 95, so we can in the beginning like inject a lot of energy, and that decreases because it heats up. And this is the sort of delta T between the bore heat exchangers during the discharging, and this is the temperature in the storage. And one of the things with the bore heat exchanger that can withstand 95 degrees, it's a certain type of plastic which is different than the standard bore heat exchanger, and it has a low thermal conductivity. So it means that the heat exchange capacity per meter of well length is a bit less. And this is how it looks like if you look in temperature difference. So we will operate like with a relatively, this is about 6-7 degrees in the beginning, and you would decrease it to about 3 degrees. So that's in and out temperature. And this is the storage temperature again. So we would go down to about 58 degrees. And it's designed to deliver about 1.5 megawatt throughout the winter until we reach the plateau here. It should be about in February, beginning of March, where we cannot supply so much energy anymore because the temperature gets too low in the storage. This slide helped the company a lot. I removed the prices because it's a bit sensitive. We can probably present after they finish it and they have some results. But alternative 6, what I've chosen, this is the efficiency that they expect. So 52% over the first 10 years. The first 3 years you have to inject a lot of energy in order to get like a warm belt, and then you get a stable running. And then we compare that to the investment cost for the subsurface part. So for the installation, the drilling, and the bore heat exchangers and so on. And we gave them a price. So it's like per efficiently retrieved kilowatt hour of thermal heat, you have to invest so much krona or euro. And this is another one here to compare 2 different casing lengths. And this is like the total investment cost. In red, you see the overall efficiency over the first 10 years. And in blue, you see the actual efficiency that we calculated in year 10 when everything is stable. So you see that you lose a lot of like efficiency in the beginning because you have to heat it up. And the idea would be, the lines are a bit, they're not helping so much, but it's about 67% efficiency in year 10. But we know that in reality, the simulations are always a bit optimistic. So I think if we have 60%, it would be nice. And then the last slide, like some thermal contamination, how can we prevent this to some extent? How can we protect the trees? Actually looking at insulating the first 10 meters of the casing. So what we do, we drill, we install the bore heat exchangers, and then we will apply afterwards an insulation in the top. So we can prevent some of the thermal interaction between the clay primarily. And then you have to imagine that there are trees standing here, there are 3 roots. And on top of this, we still have like 60 centimeters of another insulation, but that prevents like snow melt and like thermal energy losses through to the sky basically. And this is something we're still working out a bit in practical with the drilling company that has been chosen with another like an subcontractor. But we believe we have a solution for this. And it's of course interesting to see how this will turn out in reality, because it's a theory and now we have to put it into practice. Possibly also during the winter when it's cold. So interesting to see how it works out. If you have questions, you can ask me, or you can ask Sigmund, who is the project owner in Halfmond Oslo Celsius. Thank you for your attention.
Thank you, Robert. It's really interesting to see the plan for the district heating company. Then they show Statkraft's plan in Trondheim, and tomorrow we also will hear about the Kvitebjørn in Tromsø. So hopefully next GeoEnergy conference we have more than planned. Also some more. That some of them have been relocated. Some question to
Hi, thank you for the presentation. When looking at the slide, there was also alternative 5 was supposed to be also quite efficient, right? So what was the difference between alternative 5 and 6?
The difference is primarily we have two different depths, 100 meter and 150, and then we have heat borehole spacing, and it's chosen in such a way that it like we optimize the available space with the number of boreholes. The thing is that we have about 100 more wells, which also increases the price, like the investment cost significantly. And this project is more a pilot who needs it distributing company, because if it actually works, they could plan for a substantially bigger system. And so this is basically risk reward. And there's also you increase the likelihood of drilling with the boreholes like into one another. It is was specified in the drilling tender as well that they had to use a certain method to like minimize that, but we also know that there are different geologies and fractures. And then, for example, if you with the normal drilling you hit a fracture, you often get a little bit of a deflection with the method that's used in Norway. And with the different geologies and then the well logging that Ruud and I did, we expect a little bit of a spaghetti. And if we do it like have the wells too tight, then we have too many wells drilling into one another. That's basically that we have combined two in one. Yeah.
what is the borehole heat exchanger? Is that coaxial or is there?
It's like very traditional and simple and single YouTube. We had looked also at a coaxial, but since also looked into the water quality, and they expected actually a bit of scaling, so say line scale, and then that like both are like affected, but it would affect the coaxial a bit more, was their conclusion. So that's why also Celcio asked us to only look at this for this alternative, and there's a Norwegian supplier that can deliver this.
Also, the thermal conductivity, we say it's various geology, but it's so highly sensitive to what's estimate you make for the thermal conductivity of this.
Yeah, they performed, I think, 3 different thermal response tests, and they were relatively similar. But one of the things is also that's constrained here is that the thermal conductivity or the ability of the heat exchanger to exchange heat is a bit lower than the traditional ones on PE or maybe PEX. So yeah, but that's to make sure that they can withstand 30 years of 95 degrees at a given pressure. Yeah.
Thank you. I think we are quite eager to get to lunch now, so there are some more questions.
One question. Do you know if there's any process going on concerning regulation when heating up the ground? Regulations and biota, or especially when there's circulating water.
You have to treat it as Milieudirectoraat is responsible for it, and you have to treat it basically as a pollution. But we're also like in discussion with them, because I would like to like really. I come from the Netherlands where there's like very strict regulation, maximum temperatures that you can inject, etc., etc. You need to run at a certain efficiency. And then coming to Norway, it's like it's a bit of a gray zone, and yeah, it's also why we're now in contact, or at least I'm trying to get into contact. It's like they don't really know the answer as well as the feeling I have, but I would like to like get an answer and like get it clear, because this is like one of the first projects where we're like really looking at high temperature storage in Norway, but I expect that we will have a lot more. So it's good to have like a clear reference and guidelines. Because if we would do it like the first few projects wrong, then it gets like a bad name, and then it's difficult for the future to continue with it. So it's like important that we do it well.
Thank you very much. We will have the. You will say something before voting.
Should I say it or? I would like all session one, like first of all, say thank you to all participants in session 1.